Okay, so I started recording, and so I'll post this. I think I have a couple that I still need to post from last week. Uh, okay, so once you get into the idea that you have distributed simulations, you might be able to make the next jump to what we're going to talk about, which is multi-resolution simulations. And the oh, no video has been detected. Okay. There we go. Okay. So think about how things work in the real world. Company A builds a simulation, company B builds a simulation, and then some customer comes along and says, you know, it would be a great idea. Rather than me spending all this money and building a simulation from scratch, why don't I use the one from company A and the one from company B and put them together? It's just software. How hard could it be? So that's where you get this idea of multi-resolution. You can also get it in another way. Let's say you're interested in detailing things at a fine level, like a traffic study. You want to do car by car by car. And then it turns out that a lot of times car by car by car is boring. So what you might do is a high-level aggregate traffic situation. And then when something interesting looks like it's going to happen at some particular region, you drill down to that region and create a new simulation just of that region that's at the car by car level. And I'll give you an old example of this. I'll give you two. There's an old Avalon Hill game called Jutland. Look it up. And in Jutland, which is a recreation of the Battle of Jutland in 1916 between the British and the German navies in World War I, you start out in a little map of the North Sea, and you draw a pencil line of where your fleet is, and your opponent has the same map, and they're drawing where their fleet is, but you don't look at each other's, right? So you don't know where you are. And then you start saying, I was at this location at this time. And I was at this location at this time. And if it ever gets to where I say, oh, I was at this location at this time, and Jackson says, I was there too, then we get to say, that the ships have found each other and now we can have a battle. And then you move to another layer of the game where you break out the individual ships and you lay them out and you have them maneuver and fire at each other and try to sink each other. So you've got a high level of resolution where each, quote, fleet is just one entity. And then once the fleets find each other, that one entity explodes into 15 or 20 or 30 individual ships that then do the operation. Avalon Hill produced another game called Midway, Battle of Midway, which does the exact same thing. You start out with your ships on squares, and then when they find each other, you send your aircraft out and you play out the aircraft attack on the ships on another lower resolution board or a finer resolution board, individual ships, not individual aircraft, but in groups of aircraft. So this is a fairly common, or I should say old technique. These games I'm talking about are 67. John came out in 67. How long ago was that? 65 would have been 60 years ago, 58 years ago. So twice as long as you've been on the earth. Okay, it's an old technique. And why would you do this in simulation with modern computing model simulation? One is, like I said, sometimes you have two existing models that you want to mash together into a single simulation. But if you were developing this from scratch, why might you do it? In the traffic model, why not just have all the cars all the time?
Well, you're trying to find the point of interest, right?
Yeah, exactly. Yeah. You're trying to find what's interesting in the model. And if you have all the cars all the time, you might do a lot of computation for virtually no result. So why not scale it up and use traffic as an aggregate until something interesting happens, and then just model that particular point of interest, that region, in the detail. You're able to get a lot more computations in. And even though chips are really fast and memory's cheap, and we don't worry about computational cost as much as we used to, or memory footprints as much as we used to, there are still times when it is meaningful. And particularly in a situation like this, it's useful to save computation costs. Because if you break down into, I've got 30,000 entities all the time, I might be doing billions and billions of computation for no reason at all. If you look at how hierarchical organizations, and the military does this a lot. Again, they'll do it in the real world, and they do it in their simulations. They'll have simulations at the Army Corps level. They'll have simulations at the battalion level. They'll have simulations at the individual unit, individual vehicle, individual soldier level. And you can imagine how they might be interested in, oh, okay, I want to do a battalion level simulation. And that battalion level simulation, I'm moving platoon-sized units around. And it's only when the platoon-sized units get close to other platoon-sized units of the opposing forces that I'll break it out into the individuals. They'll do that thing partly because for computational costs. They may also be doing it because it just makes the training more efficient. If you're trying to train somebody, again, think about what you want them to do. When you're training somebody, you want them to go through the interesting parts of the scenario, right? You don't want to have them sit through hours and hours and hours of, in the gaming world, they call it grind, where there's no benefit. You want them to get to the part of the simulation where they're doing something and making decisions and learning how to do whatever the simulation is teaching them how to do command and control, how to do logistics, whatever. However, how to handle doctrine. You've experienced this in class, right? You sat through classes and the whole lecture is like, why am I sitting through this hour of lecture? You know, what am I getting out of this lecture? So the multi-resolution simulations exist. For various situations, for various reasons. And they come with their own unique set of problems. What they have to do is, if you're going from the small unit, and I'll use military stuff a lot. So let's say you have a simulation of a tank platoon with individual tanks. So there's 4 tanks. And now you want to represent that tank platoon as a single entity in another simulation in a higher resolution, lower fidelity, higher level simulation. You have to do something called aggregation. You take those 4 tanks, you take their positions, you average them, and you say, okay, that's where this unit is. It's in the center of mass of the 4 tanks, let's say. And then if you want to take that single entity and pop it back into the finer resolution model where the individual tanks are represented, you have to do what's called disaggregation. So it's aggregation, disaggregation, which is commonly called add-disag. In the last semester, this last year, in our capstone projects, we had a project, I wish I could remember the topic, but we had a project where they were doing simulations, and they were actually doing a multi-resolution simulation. And they had, you know, we had poster day at the end of the semester, poster day in the atrium, and I'm walking around talking to them, and I'm like, oh, and they said, oh, we did this, blah, 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 blah. And I said, oh, you had the ag-disag problems. And they knew exactly what, and they're like, yeah, we did. And they were so excited somebody knew what that was, you know. So why is this a problem? Here's the problem. Where do you have the most information? I'm representing the tanks as a single entity, 4 tanks as a single entity, or I'm representing 4 tanks as 4 individual tanks. Where do you have the most information? Higher or lower?
Lower, right?
Lower, right. You know exactly where the tanks are. You know exactly if one of the crew members is sick, you know which tank has which sick crew member. If one of the tanks loses its tread, you know which tank loses its tread. You know their positions. At the higher level, all you know is their center of mass. So let's say you have tanks that are in your disaggregated mode, and tank number 3 is injured. And so now you aggregate, and all you know is you have 3 tanks. Then you disaggregate again. Is the same tank that was knocked out before the same tank that you're going to claim got knocked out when you disaggregate? In other words, I've got tanks 1, 2, 3, 4, and tank number 4 got hit and or damaged or whatever, and it can no longer participate. So now I'm down to 3 tanks. So I aggregate, I'm down to 3 tanks. Now I disaggregate, I have to go back to 3 tanks. I know that much. But is tank 1 or 2 or 3 or 4 the one I should leave out? I don't know. I've lost that information. And you can say, oh, well, you should keep notes on that information. What you're saying is you didn't aggregate, right? If you keep all the information, then you're still at the lower level. So you get these interesting problems of how do we either, it's basically a dead reckoning problem. If I can't maintain the information, how can I try to replicate the effect of the information in such a way that it's okay? For example, let's say we had 4 identical tanks. One of them gets knocked out. You aggregate and then you disaggregate, and you're not sure which one got knocked out, so you pick one at random, and the other 3 are what you put in. That probably doesn't affect the simulation that much because they're 4 identical tanks. Now, what if you're putting in effects of, I don't know, one tank had a lot of gas and all the other tanks were almost out of gas, and the one that had a lot of gas is the one that got knocked out. Now the other tanks are going to run out of gas soon. How do you model that in the ag-disag situation? If I maintain all the individual gas levels, if I maintain all the individual ammunition levels, if I maintain all the individual statuses, I've not actually aggregated. So you have to make some choices, and you have to accept that if you do an aggregation disaggregation cycle, you are probably going to lose some information. That information might have an effect on the simulation. It might not. It might. So you come up with protocols to try to go through this process in a way where you have a good chance of maintaining continuity. These things come up again. I don't play games, but I'm aware of them. Online games, I'm aware of them. And they do the similar thing in the gaming industry too, right? So you start out, you've got, it's medieval Europe, and you've got an army marching around, and the army is marching around as a unit. And as soon as your army comes up against some other army as a unit, it gets disaggregated into its component structure. And then you fight the battle at the unit, right? The smaller unit level. That's a common occurrence in the gaming world. And it's a common occurrence here too. Why are they doing it? If you tried to model everything at the individual level, you're, number 1, wasting a lot of computation, and number 2, you may not be able to have computations that occur in a timely way to support the training that you're trying to do. Okay, so it's an interesting problem. It is technically a non-solvable problem in the sense that you can't, a computationally solvable problem means you can come up with 100% correct solution 100% of the time. And in this sense, you can't. It is a non-solvable problem because you don't have enough information. However, you can try to come up with techniques where you are getting close enough so that the simulation is still effective. Then it can get weirder. right? So one way to try to bridge that gap is this cross-resolution technique where you're kind of monitoring high and low at the same time. And the reason you might do that is you might have, again, think in terms of distributed simulations. You may have a high level simulation going on at one level, and at the same time, a low level simulation going on at other servers. Why would you do that? Maybe you're actually training a large group of people, and you're trying to train the high level officers how to manage brigade level, corps level type activities, and you're still trying to teach your unit commanders how to manage platoon-sized units or individuals. So you might run the simulation in parallel because the high-level people don't need to know all the details. Patton said, the Army commander should command the divisions and know where the regiments are. The divisional commander should command the regiments and know where the battalions are. The regimental commander should command the battalions and know where the platoons are. Right? So you always command one layer down. Right? So the high level people, they don't need all the detail. They need to see a simulation at the high level. Well, if you have this cross resolution, you're representing, say, the platoon of tanks again, both as an individual at one node in the overall simulation and as individual tanks in the other. In this case, there's no true ag disag, right? You're maintaining both. So you're not saving the computational cost. But you can have what we call temporal inconsistency and mapping inconsistency. So temporal, as you would expect, two or more conflicting views of the simulation entity state, and that's resulting from the different views of the simulation time. So at the high level, maybe I'm concerned about every tick. Remember, every tick is a cycle of a simulation. Maybe every tick is 15 minutes. And at the low level, every tick is 1 second. Well, 1 second, 15 minutes, what is that? 60 times 15? 900. So there's 900 ticks at the low level, is 1 tick at the high level. You can imagine while we're waiting, it ticked 780, that low level entity has actually changed its position, and the high level entity hasn't actually gone through an update at all yet. So you have a temporal inconsistency. You have the ability for these things to be different in the two representations. That can be a problem. I may be making decisions at the high level that don't make sense based on the low level actual, I don't know about actual, the low level representation. You can also get issues not just in time but in mapping. So you can get the temporal inconsistency is at the low level, it's like, hey, we did a lot of stuff, a lot of time has passed. And at the high level, well, no time has passed at all because it passed in 5-minute chunks or 15-minute chunks, right? So even though you've experienced 10 minutes of time, I haven't. Right? So we have a different view of time. And then that can lead to the mapping inconsistency too. And part of that can be, part of that is about aggregation and disaggregation. Part of that can be about updates based on the temporal inconsistency. So the aggregation disaggregation problem, as you would expect, comes in where I say, okay, I've got my 4 tanks, I know exactly where they are, I aggregate, and now later I disaggregate. And even though they haven't moved, I can't put them in the same place again because I've lost that information. So I can have different, I can have inconsistencies in where I think these things are. Oh, and by the way, if I told somebody else where they were, and now I do aggregation, disaggregation, they've magically moved, right? How does the other processor know that? This problem is, again, not really solvable in the computer science sense. You can get you can try to create techniques where the effect is minimal. And I've got, by the way, in addition to these short lecture slides, I've got this multi-resolution simulation paper. It goes through all of these things. It's a fairly old paper, but I think a pretty good one. These topics, I'm going to go out on a limb and say you've never had to worry about them before, that they're new thoughts. Some of these, it sounds like you had to worry about some of these before. Right? But for the most part, people aren't exposed to this until you are actually forced to, right? It's not something that, standard computer science curriculum, we don't go through this, because it's a subset, it's part of the simulation community. Unless you have a degree that actually goes fairly deeply into the modeling and simulation aspects of computer science or big data, then you don't run into these things that much. Yeah.
For the temporal inconsistencies, would it be best to have as many intervals as possible so you could mesh data within the, like, if you look at the time frame, all these
right. Right. And that's the heart of the issue. How do I make the time frames at the high level small enough where I'm getting pretty accurate estimations of what's happening at the low level without still wasting computations? Now, if you're trying to merge two existing systems, you're just screwed, right? You're just stuck. And you may have to find a way to create an intermediary system. By the way, a common way to make two systems work together is to put an intermediary in between them that you build. And maybe you have an intermediary that tries to do that meshing, the smaller meshing, so that when it goes to the update at the higher level, it doesn't have to make as big a jump. It's a possibility, right? Pardon?
Is that, I can't say the word.
Synchronization?
Yeah, is that
it's like that, yeah. So yeah, and what you can do, you can always take at the one that has the big time steps, the 5-minute time steps, let's say, you can always have it poll the one that's updating every second and say, where are you now? And then actually get the true result of where you are now. The problem with that is in a simulation that may defeat the purpose, because now you've got units that are jumping. They're magically jumping, rather than a nice smooth movement through the terrain, you're jumping around, and then humans are going to look at that and say, this simulation is garbage. I'm not going to trust it. So you've got these human factors kinds of issues that you have to pay attention to. Now, having said that, yeah, sometimes you just have to jump. Now, again, I don't play online games. Sometimes I get people who do, which is great. So I don't know if you experience like characters in a game jumping around, right? They were here and now they're, does it happen?
Yeah.
It happen a lot? I don't know what a lot means. Enough where you noticed it, right?
Yeah.
Is it getting better over the years? I mean, and here's where they're getting better. It's mostly about faster transmission speeds, right, than computation speeds. Okay, then the aggregation disaggregation issues bring up, again, these are solutions to a problem. And every solution brings in new problems. So what was the original problem? The original problem was, look, if we did everything at the high level, we didn't get the information we wanted. If we did everything at the low level, we wasted so much computation that the simulation is unwieldy. Or maybe we can't even, if it's human in the loop, maybe we can't keep up. And so we have to cheat and do high level and only bring it down to the low level when it's of interest to the human. So that's the aggregation disaggregation is the solution to that problem. But it introduces new problems. As we've already seen, it introduced the idea of the temporal inconsistencies, and it introduces the idea of the mapping inconsistencies. And now we've got these issues too, which are that takes time to do the transition. If you're going from aggregation to disaggregation, it takes time. Now, again, in human terms, the time might be, a half a second, 500 milliseconds. But think about that in computer terms. How fast is your chip? How many cycles can your laptop do these days? Like 2 gigs or something like that? That's my computer. It's old. You guys are faster. You guys always have better computers than me.
My desktop, I think, is 4
gigs?
Yeah.
Yeah. So think about it. In half a second, that's 2 billion operations that you're missing out on. Right? So in human terms, it's a blink of an eye. In computational terms, you're missing a lot of computation. That's for the ag-disag. Then, not only do you have the transition latency, then you have the latency across the network too, which is going to be even bigger than the computational latency. But worse than that becomes what we call network flooding. So if you had a high-level entity and it contains 1,000 individual entities, and now you do the disaggregation, you've just introduced 1,000 entities into the simulation. Each of those entities is going to say, here I am, and send its heartbeat message out to the RTI. Right? It's going to send its message out to the rest of the world to let everybody know that it exists. And guess what? And you can see why it's called network flooding, because now you are just too many messages all at once. You can also get, and unfortunately for the people online, this is going to be on the board. Yeah, the way this works is this way. I'm at the high level, and I say, okay, here's my entity. And then here's somebody else's entity. And we've all got a radius that we're interested in. And if that radius overlaps, then we're going to disaggregate and say, okay, now I'm going to show you my individuals. And they're going to say, we're going to show you our individuals. Okay. So you can see this transition from the high level single entity to the low level multiple entity. That's where you get the transition latency, right? Particularly if this thing has a lot of entities. That's where you can get network flooding. But then you can get thrashing. And the thrashing occurs because you can have the notion of, oh, here's our area of interest. We bumped into each other. So we have to disaggregate because now we're going to interact at this more intimate level. And everybody here has their own area of interest. And it is possible that at the high level, they overlapped. And at the low level, there's a gap. They didn't. Well, if you're at the low level and there's nobody around you that's of interest, what would you do? Aggregate. So now they both aggregate. And now if they're aggregated, they're like, oh, we bumped into each other. Let's disaggregate. This is called thrashing. Thrashing is when you do any activity back and forth. So now you disaggregate. Nobody's near. Aggregate, right? You can also do a thrashing, a form of thrashing that can show up if you have movement. And during the movement, I come within this zone of control or this sphere of influence and I disaggregate. And then as I'm moving, I come out, right? Now I'm here and I'm out, so I aggregate, but then I come into this one, so I disaggregate. Then I move a little further and I'm out, so I'm within this one and I aggregate, right? So just the fact that you are moving through the map, you may accidentally come into situations where you have to aggregate and then disaggregate, aggregate, disaggregate. And again, that's a form of thrashing. Thrashing is a generic term. Anytime you're doing rapid cycling back and forth with something, that's called thrashing. there's a form of what's the memory thrashing that I can't recall the mechanism for. There's a memory thrashing where you're pulling from memory and ignoring it, dumping it back in, pulling from memory, dumping it back in.
Like a leak?
Hmm?
Memory leak?
It's not a leak.
No.
It's not a leak. It's weird. I may or may not get it by the end of the lecture. It's not that important. But that's the idea of the thrashing. Right, again, so this idea of aggregation, disaggregation, it solves a great problem. It introduces these new problems, as all things do. You can also get chain disaggregation, which is the fact where the fact that you disaggregated one thing means that you got others involved. So here I am with my entities, and each one of them has a zone of interest. Okay. And there's gaps here. So the fact that they're separate from each other, they don't have to worry about running into each other. They don't have to worry about interacting with each other at the detailed level. So they're all at their high level. But here, these guys bumped into each other. So now we're going to disaggregate. So we disaggregate this guy, and we don't know, remember, we don't know where the actual positions are, so we have to guess. And then this one gets disaggregated. And maybe we put one of these guys out here. Well, now, here we are. I've got my zone of control or my area of interest. And this area of interest got extended because of how I placed that thing. And now I'm in here. So now I have to disaggregate this one too. So I disaggregate this one, and the way I disaggregate it, I happen to bump into this one's zone of control, so now I have to disaggregate this one too. It's called chain disaggregation. It's a chain reaction. The act of disaggregating one could put one of your local entities in this area of interest of the next one over. And so you can imagine again, let's do, I don't know, commercial ships in a port. And the ships look like this. There's a little convoy, and we aggregate that, and we call it this, and we say, here's its area of interest. But you can see that when you spread it out, it's actually got a wider area of interest than your aggregated version. So just by disaggregating, you've expanded it, literally geographically expanded it on the map, which means that its area of interest or its area of concern is further out than at the aggregate level, which means that if I had another entity here, I'm going to violate that boundary. And if I violate that boundary, then I have to disaggregate the next thing. So you, again, think of have you ever seen a map of World War I trench warfare? Like here's France and here's all the trenches, and they always show them like at the Corps division level, right? So you've got these big chunks. And if you disaggregate one, think of that whole line all of a sudden up and down the whole line of trenches, you have to disaggregate because you disaggregated one point, which put a unit out into the field of influence of another, which now needs disaggregation, which did it again, which did it again, which did it again. So you could see, you could have these perverse situations where you're just creating thousands and thousands and thousands of entities at the lower level simulation all at once because of this chain disaggregation problem. Yeah.
Then what do you want to reflect the sphere of influence of all of them in the tiny point?
Right. So you have to be careful about how you develop those rules. And as usual, there's no perfect solution. So let me give you an idea. Let's say I had, and I don't even know what we're representing. Okay, so I'm going to represent these three. There's 4 circles, and here's the center of mass. Okay, so when I aggregate, I'm going to say, okay, there I am, and there's my center of, and I'm going to put this at the center of mass. Now I'm going to do these four and their center of mass. So I'm going to put that at the center of mass. But you can see these 2 points here and these two are, they're going to result in the same effective center of mass, right? But these 2 points on the horizontal line are way out here. Now, do I have that information at the higher level? No. That's the point of aggregation, right? I don't keep track of the individual members. Could I tag it? Could I put metadata in there? I could. But be careful. If you do that for everything, what you've got is the lower level model still. So you have to be careful. But yes, you could put center of mass and radius, let's say. Right. There are no wonderful solutions to any of these things. Okay, so that's a quick tour through the idea of multi-resolution simulations. And where will they come up? You may or may not in your professional career work with simulations. So you may or may not have to worry about this in the context of what we're talking about. But even outside the world of simulations, these kinds of things can show up. Companies, as you know, buy each other out all the time. And every corporation keeps track of its employee database and its sales and blah, blah, blah through databases. And so when they buy them out, they want to combine the databases. Some of these problems show up. At what level of detail were the databases kept? If there's one company keeping records at a different level of detail than another, you've effectively got these aggregation, disaggregation problems. How can I try to make these databases work together? By the way, that's a very lucrative job. I have a friend who made his entire career being a consultant for companies that are trying to combine databases. And as you know, consultant is better money than being hired as an employee, right? You don't get the health benefits, but you get the larger paychecks. So, but yeah, he's spent his whole life in, for the most part. So these problems do show up outside of simulation. They're not the common stuff like that we try to teach you in your 4 years here. You know, we're trying to get you through basic programming, but also I try to get you to be aware of what real world problems do exist out there. These become real world problems. And I think that's all we need to talk about for the multi-resolution simulation stuff. Read through that paper though. Every now and then, you know, I have the papers that I put in here, they're all at least 10 years old, but they're most of them are good to really good. Let's put it that way. And this one's really good. That one that Bonobo did about agent-based simulation, really good. Yeah, this one's also real good. So yeah, read through it. Do we have questions or comments, or did I say anything confused you? Okay. As an aside,